Hi everyone, I'm Antonin Martin-Schouler.
And I'm Nicolas Dumini.
In this video we will present you our project, the Globe of Persistent Vision. For this project we worked here in the Fab Lab of Telecom Bretagne called the Telefab. As you can see, it's a place full of tools where anyone can come and work on this project and where all the members are ready to help.
We spent the last 6 months working here and building our product, and after a lot of efforts we are ready to present it to you.
As you can see, the previous version of the globe had a poor resolution and its brightness was very low. Also, it was very noisy. Therefore, it was decided to build another one.
Now, let's see the second version. After checking the different links, we connect it to our PC using a serial communication. Our Linux is working on the ARM processor of the Zinc. It loads the module and the applications it needs automatically after booting. Now, if we enter the /mnt folder, we find several files including our applications. I can launch, for example, the Olympics application. And there it goes. You can notice the two lines device opened, which tell us the corresponding drivers are used. The former managing the motor speed, the latter the control signals. We can stop the application whenever we want. The drivers will be released. For now, we have developed 5 applications. Gyro, or the Olympics, displays the rotating image of the Olympic symbol. Word is the equivalent of the first application any programmer has written, except that the Hello World is displayed on the globe. Long word displays a very long text by making it appear on the globe using a sliding window. The last application, Speed Controller, can set the speed of the motor between 0 and 255. We can use it to stop the globe, for instance. So, how does globe work? We use a LED strip put on a rotating ring to give an impression of a full globe of pixels. Then, we change the pixels in synchronization with the globe rotation to display the columns. We can display images at a resolution of 100 per 49 pixels. The strip needs 32 bits per pixel sent with the serial protocol. The 8 first bits are global values, which let 24 bits for coding the colors. As the last version of the globe used a slower LED strip, we had another LED strip on the other side of the ring, which displayed the opposite column. The idea was to double the frame per second rate without changing the rotating speed. As you can see, the LED strip on the other side is hidden under adhesive tape and is currently kept only to balance the rig mechanics. What are the key pieces of our globe? This infrared barrier enables to synchronize rotation and display. The slip ring connects electrical to steady in the rotating part.
The electronic architecture of the globe, implemented on an FPGA, is divided into 3 parts. The first part is the display controller, composed of the column reader, send pixel, and send to stripe. It's the part which will convert a picture into signals understandable by the LED strip. The second part is the 2-frame buffer, in which the pictures are stored. The advantage of having 2 frame buffers is that you can display a picture from a frame buffer while writing another one in the other frame buffer. The last part is the interface, composed of the GPU and the write and read image. This part is in charge of the control of the picture. It can initialize the frame buffers, rotate the picture, or control the displaying of characters. Finally, we had several signals in order to make it controllable from the processor.
The extension board is also important. You can see here the scheme of the board. It fulfills 3 functions. First, we must supply power to the system. FPGA, LED strips, motor, sensor, using one of several power configurations. Then, we must control the motor rotation, only in speed, using pulse width modulation. Finally, we must convert the 3.3 volt signals sent by the ZIBO into 5 volt signals received by the LED strips. Let's finally talk about the globe mechanics. You can see here the globe mechanics design. We can split it in 2 parts. First, the rotating part, which contains the rotating ring on which we stuck the LED strips. It also contains the slip ring below, its wires hidden in the hollow axis. To stabilize the rotation axis, we added 2 ball bearings. To rotate the axis, we added a pulley, which is connected to a motor with a driving belt. You can see here the complete structure of this part of the globe. As I said, the rotating part of the globe is driven by a motor thanks to a belt. This motor must be held to the structure as to optimize the globe rotation. For that, we designed metallic presses. To decrease the impact of the belt tension, we extended the motor's axis above the pulley and put a ball bearing on it. The whole system can move on a road structure as to set the driving belt tension or to correct the pulley's alignment.